Hi class, Dr. Searcy here with the video lecture for the Chapter 8 odd numbered problems. I just noticed right before I started this video that when I created my lecture notes that I forgot to type in that these were for the odd problems. I would go back and redo everything, but I don't want to redo everything that I've written. This is about 7 pages worth of stuff, so I'm just going to keep it like this. Just know that this is the odd problems lecture for Chapter 8. So let's remember that the title of the chapter was Introduction to Hypothesis Testing, right? And in this chapter, you learned that 4-step process for how to conduct a hypothesis test. Okay, so let's go over the questions together. Let's say the first question is, identify the 4 steps of a hypothesis test as presented in this chapter. Okay, so we went over each one of those. We'll just do that again really quickly. Remember that the first step is that you're going to state your hypothesis, right? And this is where you're going to make those 2 predictions. You're going to make a HO statement. Remember that HO or H sub O was your prediction that there was going to be no effect of your independent variable, and that was referred to as the null hypothesis. The second hypothesis, or the second prediction that you will make, is your H sub 1, the alternative hypothesis. This hypothesis said that the independent variable was effective. It did have an effect on the treatment, or on the participants. Okay, so in step 1, you state your hypothesis. There's actually 2 of them. One that says no effect, the other one that says yes effect. Once you've done that, then step 2 is to locate that critical region, right? And remember, basically the idea here is that here you're going to come up with some specific z-score. And you're going to say, in step 3, I'm going to do some calculations of z's, or a z-score. The z-score that I calculate has to be greater than the z-score in my critical region in order for the experiment to have been effective, or the independent variable to be effective. Okay, so in step 3 then, let's just remember that the step is that you're going to collect data and you're going to conduct your computations. I'll just note that it should be, at least in this chapter, it should be 2 different computations. We're going to start out by figuring out what the standard error is in your experiment. But the reason why we need that is because we're then going to use it to calculate z, and we go to calculate z. Standard error is going to be in the denominator of your z formula. Okay, so first, in step 3, first you'll calculate standard error, then you'll calculate z. Once you've done that, you're going to compare the z-score that you've calculated to the z-score that you've set as the z in your critical region. And so that sets you up for step 4, which is where you are going to decide. Either your treatment was effective or your treatment was not effective. And remember, that's going to be based on how that z compares to that z. Basically, we're saying if the treatment is effective, then the calculated z is greater than, we'll say, the critical region z. Okay, so you've calculated a z here. You're going to compare it to the critical region z. If your calculated z is greater, right, if it's a bigger number, then your treatment is effective. On the other hand, if the calculated z is less than the z in the critical region, then you're going to decide that your treatment was not effective. Okay, so let's go ahead and move on to question 3 then. Question 3 is going back and asking about these 2 errors that the researcher can make. Remember that these two errors could be the errors that you're going to make in step 4. You've decided that your treatment is either effective or it's not effective. In making that decision, maybe you made the wrong decision. If you did, you've made either a type 1 error or a type 2 error. So let's just look at the matrix that explains that, right? So we said that there's 2 things that you want to be thinking about. First thing is the actual outcome of the study. What actually are the results of the study? Remember, we said that there's only 2 potential outcomes. Either the null hypothesis is true or the null hypothesis is not true. Remember, saying that the null hypothesis is true is saying that there is no effect. Saying that the null hypothesis is not true is saying that there is an effect. Along with that, you had your actual outcome of the study, but then there's the decision that you make based on what you see in the data. Here we're saying that you can make the incorrect decision, right? But first let's say, well, what's the decision? Your decision can be either that you reject the null or you accept the null. Again, remember what these 2 things mean. If you reject the null, then you're saying, so reject the null, you're rejecting the null hypothesis. If you reject that, your decision is that you say that there is an effect. If I reject the null hypothesis, I'm saying that the difference between the 2 groups is not 0. I'm saying that there is a difference other than 0, so therefore there is an effect. However, if I accept the null hypothesis, then in my decision, I'm saying that there is no effect. Okay, so what were the 2 kinds of mistakes that you could make? The first one was the type 1 error. This is the mistake where the actual outcome is that the null hypothesis is true, right? So there really is no effect, but you said that there was an effect. And then type 2 error was saying that there is an effect, but you decided that there was no effect. Of the 2 types of error that are really bad, a lot of researchers would say that the type 1 error is the kind of error that you really want to watch out for, because it's saying that you thought a treatment was effective when it actually wasn't, right? And you don't want to do that, because then that's going to cause you to treat clients with treatments that are not effective, and you'll just be wasting everybody's time if you do that. Okay, so let's go ahead and move on to question number 5. Here, the question is reading, the value of the Z-score in a hypothesis test is influenced by a variety of factors, right? So going back to that idea that we're looking at the Z-scores. Assuming that all other variables are held constant, explain how the value of Z is influenced by each of the following. So we have an A situation first, which says increasing the difference between the sample mean and the original population mean. So I've got this kind of explained here. What they're saying is you are looking at this difference, right? So the population and the sample. In this case, it could be that before score and the difference between it and the after score, right? So the mean of the group before the treatment and the mean of the group after the treatment. Here, we're saying that if my independent variable is going to be effective, I want there to be a big difference here. I want the group to look different after the treatment than they did look before the treatment. So let's say that I do see that difference, and it's a big difference. It's a larger difference. What does that mean? What's that going to mean down the road? Well, what it means down the road is that that's going to give you a larger numerator in your Z equation. We'll say in Z equation, right? It's going to be a larger number on the top part of the division problem, that is your z equation. Remember z equals your sample mean minus your population mean over what we've been referring to lately as the standard error. So we're saying that difference is that difference in the numerator. If it's a bigger difference, then that's going to end up giving you a larger z. How's that going to happen? Well, we've got two z-scores that we can compare here, right? So we have a z equation here and a z equation here. Which z equation has the larger difference in their numerator? The 6 minus 4 or the 10 minus 4? Well, this is the z equation with the larger difference, right? 10 minus 4 as opposed to 6 minus 4. You get a 6 in the numerator here versus a 2 in the numerator there. What does that end up doing to the two z's? It gives you a larger z here and a smaller z there. So the whole point of that is, right, remember we're saying, at the end of the day, when I go to my step 4 and I make my decision, I'm going to decide that my treatment was effective if my z that I've calculated is greater than my z in my critical region. How can I make sure that that's going to happen? I can make sure that I have a large difference between my before score and my after score. Okay, so let's go ahead and move on to 5b. Here it says, increase in the population standard deviation. How's that going to influence the data? Well, what we have here is the scenario where that happens. Let's say that the standard deviation does get increased. That's going to lead to a larger standard error, right? Because remember, the standard error equation is standard deviation over the square root of n, right? So if you have a larger standard deviation in your numerator, that's going to cause you to have a larger standard error, and that is going to lead you to having a smaller z, which is bad. You don't want a smaller z because then you're going to have trouble getting that z to be greater than the z in the critical region. So let's just look at a couple of examples where this happens, right? So we have two equations that start off with standard error, then with standard deviation, then standard error, and then they lead to your z equation. Okay, so what ends up happening here? I have where I'm starting off with a smaller standard deviation and a larger standard deviation. I run both through my standard error equations. Over here, I get a standard error of 1, and here I get a standard error of 4. Notice how this is where we're saying if standard deviation increases, then I get a larger standard error. Standard deviation increased, caused a larger standard error. What did that end up doing to my two z's? I got a z here and I got a z here. The z that had the larger standard deviation ends up being the smaller z, and that's what we don't want, right? So when you go to conduct your experiments, just think that I want standard deviation that is more decreasing as opposed to increasing. Why? Because a smaller standard deviation is going to end up leading to a larger z. Okay, so then we've got 5c. How are numbers affected here? Here we're saying increasing the number of scores in the sample. Well, if you increase n, that's going to cause you to have a smaller standard error, right? Because your n went there. And if you have a smaller standard error, that's going to lead you to have a larger z. Here we got a couple of examples of this. Notice that we got an example here, and we've got an example here. What's the difference between the two? This example, we've got a small n. Here we've got a larger n. Which n ends up having the larger z-score? Well, here we have a z-score of 3. Here we have a z-score of 6. Right? So the 6 is the larger z-score. It's also where there is the larger n. Okay, so now let's go ahead and see how all this works in terms of actually conducting a study and then running through the 4 steps to find out whether your independent variable was effective or not. Here we're saying that we've got a study, we've got an experiment. Actually, I don't think this is an experiment. I think that they're just looking at they're looking at a situation where they did not manipulate any data. So let's see how that happened. We've got a study by Babcock and Marks in 2010, reviewed survey data, right? So they didn't do anything to anybody. They just asked some people some questions. So this is a non-experiment here. But what they did was they set it up as if it were an experiment, if this variable was going to have an effect. Okay, so what did they do? They reviewed survey data from 2003 to 2005 and obtained an average population mean of 14 hours per week spent studying by full-time students at a 4-year college in the United States. Okay, so far what they're saying is we looked at how much college students studied, and we found that the population that we looked at studied an average of 14 hours a week. To determine whether this average has changed in the past 10 years, the researchers then selected a sample of 64 participants of today's college students and obtained an average of 12.5 hours. Okay, so they didn't administer a treatment, but they did look to see if this sample of students who said that they study an average of 12.5 hours a week, look to see if they are significantly different from the population that says they study for 14 hours a week. Okay, so what we're seeing here is that there's a difference between the 2 groups, but what we're asking is that difference meaningful? Is it statistically significant? So what we're going to do is we're going to run through the 4 steps, but we need to get some more information. One other piece of information that we need to get is how many students there were in the study. Here we're saying that there were 64 students. We also need the standard deviation for the distribution. It's a 4.8. And then they're asking the question, does this sample indicate a significant change in the number of hours spent studying? And then they're telling us that we're going to use a 2-tailed test with an alpha of 0.05. Okay, so what does all that mean? It means that we need to look at the results of the study in terms of the 4-step hypothesis test. So remember, the first step in the hypothesis test is that you are stating your 2 potential outcomes. Your hypothesis of H sub O and your hypothesis of H sub 1. Remember that the H sub O was your null hypothesis and your H sub 1 was your alternative hypothesis. And the other thing that you want to remember about these 2 hypotheses is that H sub O is the hypothesis that was saying that, or your prediction that there was going to be no effect of the IV. H sub 1 was your prediction saying that there will be an effect. Right, and how are they saying this? They're saying that there's going to be, this is a statement of no effect in that we're looking at that 12.5, but at the end of the day, the 12.5 is actually equal to 14, or at least the population that represents that 12.5 is actually a population that did study for 14 hours. This is just a sample that's off of that. However, the alternative hypothesis is saying that no. These students' study hours represent how many hours students are studying today. So now the new hypothesis is not, or the new population average is not equal to 14 hours. Instead, the new population average is equal to this 12.5 hours. Okay, so that's your step 1. You've stated your 2 hypotheses. Now step 2 is you're identifying your critical regions. Basically, the way that you're setting this up is you're saying that your alpha is at 0.05 as a 2-tailed test. So what you've done is you've said, okay, because it's a 2-tailed test, I'm going to look to see if the z that I calculate in step 3 is going to be in this region or if it's going to be in this region. We're saying that those two regions that I've just shaded in total 5% of the curve. But we have to split that 5% up, right? So half of it's going to go here. The other half is going to go there. So in actuality, this is 2.5% of the curve and 2.5% of the curve. If you were to look up a tail of 0.025, you would see that the z for each of those is a positive 1.96 there and a negative 1.96 there. So what we're saying is, when we go to calculate our z, in order for our treatment to be decided to be effective, the z that we calculate has to be more than 1.96. It has to have an absolute value greater than 1.96. Okay, so let's go ahead and get into that step 3 then. Let's do the equations that are necessary. Remember that the first thing that we said is that we have to calculate the standard error. Why are we going to have to calculate the standard error first? Because we're going to need it in the denominator of our z equation. So we're going to calculate standard error. It's that standard deviation divided by the square root of n. And so that gives us a 0.6, right? We started off with 4.8 divided by the square root of 64, which is 4.8 divided by 8. And that's how we got the 0.6. So now we take that 0.6, we put it in the numerator of our z equation, and we put it in the denominator of our z equation, and in the numerator is that x bar minus mu. In this case, it's the 12.5 minus the 14. So we reduce that further to a negative 1.5 over 0.6, and that reduces further to a negative 2.5. Okay, so now what you're doing, right, is you're about to go to you've just finished step 3, you've just done your equations. Now, in step 4, you are comparing this z value that you've just calculated to the z value in your critical region. And you're asking yourself, is the z that I calculated, right, it's an absolute value, is its absolute value greater than the absolute value of the z in step 2? Here, we are saying yes. The absolute value of negative 2.5 is greater than the absolute value of 1.96. So what does that mean? That means that we reject the null hypothesis, right? So we reject the hypothesis that there's no effect, and we conclude that there was a significant change in study hours. So what we're saying is, whereas the population of students used to study 14 hours, based on the data that we've got here, now we say that the population of students studies an average of 12.5 hours, which is kind of sad, right? The number of study hours has gone down. Okay, but remember, the reason why we rejected the null was because the z that we calculated was higher than the z in our step 2. Okay, now we're going to go ahead and move on to problem number 9. I don't really like this problem because you've just been introduced to steps 1, 2, 3, and 4. And in my mind, this problem should be another problem where you go through steps 1, 2, 3, and 4. But they don't do that with this problem. Here, they kind of assume that now you've mastered what you're doing in those steps, and so now they're going to mess with you and see just how much you understand what's going on here. So I'll walk you through how they mess with you in this question. To begin with, it reads, the psychology department is gradually changing its curriculum by increasing the number of online course offerings. Wow, that's interesting. That's a thing that's changing it at our college. Anyway, to evaluate the effectiveness of this change, a random sample of 36 students who registered for introductory psychology is placed in the online version of the course. At the end of the semester, all students take the same final exam. The average score for the sample is 76. For the general population of students taking the traditional lecture class, the final exam scores from a normal distribution with a mean of 71. Okay, so in this, what they're saying is, they've got some students who are taking these online classes. They want to know who's better in passing the class, the online students or the traditional lecture students, right? The normal face-to-face. They're saying for the online kids, their final exam average score is 76. For the traditional kids or the traditional class, their average final exam is 71. Right? So here they're saying it looks like the online students are doing 5 points better than the traditional students. And what we really want to know is this actually true? Is this something that we can trust? Well, one way to get at that is to have a large enough sample, right, that's representative of this population of online students. So that's where they're going in question A. They're saying, if the final exam scores for the population have a standard deviation of 12, does the sample provide enough evidence to conclude that the new online course is significantly different from the traditional class? Use a two-tailed test with alpha equals 2.05. Oh, crap. I'm sorry. Actually, this question does the right thing. It is asking the questions correctly, I think. Let's see. Yeah, okay. So they're going to run through the steps very well. Okay. So they're going to go through the 4 steps. What are the 4 steps? The first of the 4 steps is you state your 2 hypotheses, right? So the null hypothesis, that there is no effect, that actually the 2 means are exactly the same, everyone gets an average score of 71. Or the alternative hypothesis, which says that the 2 means are not the same, the online students don't have a mean of 71. Their mean is going to be something other than 71. Okay, so that allows us to now move on to step 2. In step 2, we're doing the same thing. We're identifying the z value that we got to beat in order for the step 3 z to be significant. Right? So in step 3, we're going to go do our calculation again. The z that we calculate has to be greater than 1.96 for the treatment to be effective, for there to be a significant effect. Okay, so step 3, we're saying the first thing I'm going to do is calculate my standard error. We're saying it's that standard deviation of 12 divided by the square root of 36. And that 36 is coming from that number of participants. So when we solve it, we're seeing that we get a standard error of 2. We're going to take that standard error of 2, and it is going to become the denominator in our z equation, where the numerator is that sample mean of 76 minus the population mean of 71. So we solve that equation, and that gives us 5 over 2, which gives us a z of 2.5. Okay, now, remember, at this point, we're about to go into step 4. Step 4 is where we make our decision. Was our treatment effective or not effective? The basis of the decision is this z that we calculated greater than the z in our step 2? Here, we're saying that it is. 2.5 is a larger number than 1.96. What does that mean? That means that we reject the null hypothesis. And we say that the online course had a significant effect. Okay, but now they've got a question B here. If the population standard deviation is 18, is the sample sufficient to demonstrate a significant difference? Again, use the two-tailed test with alpha 0.05. Okay, so in B, they're changing one thing. The one thing that they're changing is the standard deviation in the standard error. They're saying instead of it being 12, now it's going to be 18. The question they're asking is, are we still going to find a significant effect? Okay, so I'm gonna for question B, I'm gonna skip steps 1 and 2. The reason why I'm skipping them is because the steps are exactly the same for step B as they were for A. Right, so we're still in step 3 going to calculate a standard error and a z-score, and that z-score still has to be greater than this 1.96. Okay, so we start off with this big difference where instead of having 12 in the numerator of our standard error equation, now it's 18. That gives us a standard error of 3. We use that standard error of 3 in the denominator of our z equation, so that now we get, we still have the 76 minus the 71, just like we did before, but now we get 5 over 3, or a z of 1.68. Now, when we go to compare this z that we've just calculated to the z in our step 2, we see that now this z is smaller than this z. So when we move on to step 4, now we have to make a different decision. Now the decision is that we have to accept HO. We have to accept the null hypothesis. And what does that mean? That means that now the online courses did not have a significant effect. Okay, so in this question, what the authors of the book are doing is they're giving us a situation where there was a significant effect, and then they're giving us a situation where there was no significant effect. What's the one difference between the two problems? The one difference is the size of the standard deviation. And they're saying then that that's going to influence whether your treatment is effective or not. And that's what we're getting at in question C. Here it says, comparing your answers for parts A and B, explain how the magnitude of the standard deviation influences the outcome of a hypothesis test. Well, when the standard deviation was smaller, we had significance. When the standard deviation was lower, we lost significance. So we conclude that a larger standard deviation produces a larger standard error. This reduces the likelihood of rejecting O, right? Exactly what happened here. We weren't able to reject O. Instead, we had to accept HO. Accepting HO is saying that you did not have a significant effect. Okay, so now let's go ahead and move on to question number 11. Okay, looks like this is another problem where we're going to run through the 4 steps again. Good, I like this. Okay, so to begin with, it says, a random sample of 25 scores is selected from a normal population with a mean of 40. After a treatment is administered to the individuals in the sample mean is found to be 44. Okay, so let me just kind of see where we're at with that. We had 25 participants in our study. The mean of the population is 40. Our sample's mean is 44. That leads us to question A. If the population standard deviation is 5, is the sample mean sufficient to conclude that the treatment has a significant effect? Use the two-tailed test at 0.05. Okay, so here's our question A. We've got our step 1, our statement of our null hypothesis, and our statement of alternative hypothesis. The null is saying that in actuality, there is no difference between the population and the mean. The alternative hypothesis is saying that there is a difference between the population and the sample. Okay, so that leads us to step 2. In step 2, we're just, again, identifying that z-score value that we've got to beat if we want to find significance. The z value that our step 3z has to be greater than. Okay, so that allows us to move on to step 3 then. First thing that we're doing is we're calculating our standard error. It's the standard deviation of 5 over the square root of 25 gives us 5 over 1, reduces to 1. So then we use that 1 in the denominator of our new z equation. In the numerator, it's our sample mean minus our population mean. So that 44 minus 40 over 1, and that gives us a z of 4. Okay, so step 3's z of 4 is compared to step 2's z of 1.96. Which number is larger, 1.96 or 4? Well, that is part of our step 4 decision. We're saying that the z of 4 is larger than the z of 1.96. Therefore, we are rejecting the null hypothesis, and we are saying that the treatment was effective. Okay, so then that leads us to question B. Now they're changing something around. Before, the population standard deviation was 5. Now it's going up to 15. Is the sample mean sufficient to conclude that the treatment has a significant effect? Use a two-tailed test with alpha equals 0.05. So again, we'll move into question B. We can start off at step 3 because steps 1 and 2 have not changed. Step 3, we're just going to rerun the calculation with this new standard deviation. And so it begins with that 15 over 25, the square root of 25, gives us this standard error of 3. Use that in our new z equation. We still have 44 minus 40 over 3 now, but that gives us a z value of 1.33. Now we go compare our step 3 z to our step 2 z, and we're seeing that this is smaller than this, right? 1.33 is smaller than 1.96. So when you get to your step 4, you've made your decision, and the decision is that you have to accept the null hypothesis. Why are we accepting? Because step 3z was smaller than step 2z. What does it mean when you accept HO, when you accept the null hypothesis? It means that the treatment was not effective. Okay, so then that leaves us to question C. It says, comparing your answers for parts A and B, explain how the magnitude of the standard deviation influences the outcomes of a hypothesis test. Basically the same thing. Larger variability reduces the likelihood of rejecting HO. I think that was exactly the same thing that happened in the previous problem. But anyway, let's go ahead and move on to number 13 now. Okay, now here's the one where, yeah, where they were getting kind of sketchy. I almost didn't even want to explain this problem to you guys because I don't like it. Now, this is that point where I was saying earlier, they're taking your understanding of steps 1, 2, 3, and 4, and they're messing with you on this. So let's see what they do. Let's see what they do. We start off saying we have a random sample that's selected from a normal population with a mean of 100 and a standard deviation of 20. After a treatment is administered to the individuals in the sample mean is found to be 96. Okay, so we don't even know what's going on here. We just know we started off with a mean of 100, a standard deviation of 20, and then for the participants that we were recruited, their mean was 96. The sample was 96. Okay, so here they're asking this funky question. How large a sample is necessary for this sample mean to be statistically significant, right? So how large of an N do I have to have here for this to be significant, for me to say that the IV was effective, to reject HO? Well, if they're asking how large a sample is necessary, basically what they're asking for is what size N do I have to have? How many participants do I have to have in the study where this is significant? Right, so we're having to move out of our steps 1 through 4. But now what you should be thinking about is, well, how can I figure out what n is? One way that you can do that is you can think about the two equations that we're working with here, right? So we have the standard error equation, and we've got this z equation. They're asking us to come up with some kind of n. So what we can do is we can take the information they've given us and we can use it inside of these equations, right? And we can use it to kind of just give us a sense of, well, what n do I need? Okay, so another thing that they're saying here is the z value that you have to beat is based on that two-tailed test that alpha equals 0.05, right? So when we go to calculate the z in this study, if we're going to do our steps 1 through 4, the z that we have to get is going to be that z that has to be greater than the 1.96. So what we're going to do to find n is we're going to work backwards. We're going to say, let's say that we start off having that z that we need, that 1.96. From there, let's say, okay, what do I got to do to get that? Well, what we can do to get that is we can punch in the information that we know that we have, right? So far, if my z equation is z equals sample mean minus population mean over standard error, so far I know that what my z is, because it's the z that I have to beat, right? I have to get better than this z, so we'll say that that's our z. I also know what my sample mean is, and I know what my population mean is, right? So I can start off the equation because I've only got one variable that I don't know the value of, that standard error. Right, so with this, I can use algebra to figure out what my standard error is. The way that I can do that is just simply, right, our goal is to isolate the standard error. And looks what I'm doing here is my first thing that I did was I solved the difference between the 96 and the 100. So that gave me 1.96 equals -4 over my standard error. My goal is still to get that standard error by itself. So what I'm going to do is I'm going to move it out of the denominator of this division problem. The way I'm going to do it is right now it's part of a division problem. So I'm going to multiply it out. When I do, cancels on that side, and I'll just bring it over and make it part of a multiplication problem on this side. So that leaves me with then standard error times 1.96 equals 4. The way I'm going to further solve that is now I'm going to move that 1.96 out. Right now it's part of a division problem, or part of a multiplication problem. So I'm going to divide it out. Cancels on that side, divided on the other side. So then I'm got a standard error of 2.04. Okay, so now I'm able to take that information and start to fill it in on my standard error equation. The way I'm going to do that is I'm going to say, oh, okay, my standard error is 2.04. My standard deviation is 20. The thing that I need to figure out is my n. Right? So now I've got this equation that I'm going to work with. To start off with, I'm going to, I'm just going to forget about needing the square root of the n for right now. Right now I'm just going to try and solve for the equation when it says 2.04 equals 20 over n. So the way that we're going to work this out, right, we're trying to get n on one side of the equal sign by itself. I'm going to do the same thing that I did up here. I'm going to start by multiplying that n out, multiplying it on this side. So now I have n times 2.04 equals 20. Same thing to isolate the n again. I'm going to now move that 2.04 out, divide it by both sides. Cancels on that side. And so then I'm left with now this n equals 9.80 39216. But notice that I've also squared it. And the reason why I've squared it is because up here is part of that, that square root. So now I'm going to take care of the squaring part. Basically what I'm going to do is I'm going to multiply this number by itself, and I end up with an n of 96.11. So now this is the answer to my question A. The n that I have to have in order to have a z value of at least 1.96 is 96.11. Right, this is kind of that situation where it's that discrete numbers versus the continuous numbers. There is no 0.11 of a participant. So what I'm going to say is I need 97 participants in order to have a z-score that's at least 1.96. Okay, so it looks like they're going to do the same thing with question B. But one thing that I want you to see here is what they've done with this question is they've just kind of messed with you in terms of your understanding of everything that's going on, but particularly they've messed with you in terms of understanding how the equations work, right? And how you can fill in parts of the equations to get answers that you need. Let's take another look at how they do this, right? In question B. Here they're saying if the sample mean were 98, what sample size is needed to be significant for a two-tailed test? Okay, so they're asking the question all over again. The only thing that they're changing is that this time, instead of having the sample mean of 96, now you've got the sample mean of 98. But you're basically going to start off doing everything that you did before, right? So you need to know, given this situation, what n do I need to have in order for this difference between the sample mean and the population mean? What n do I have to have for that difference to be significant? So the way that we're going to start answering that question is by beginning with the z again, right? We know what z we have to have in order for this to be significant. We have to have that 1.96. So we're saying, okay, that's the z that I need. How am I going to get that? Well, I've got this 98 minus this 100 over some particular standard error. So now what I need to do is figure out what the standard error is. How am I going to do that? I'm going to use simple algebra. Right? So the first thing I'm going to do is going to multiply that standard error out. Cancels on this side. Bring it over to the other side. Now it's being multiplied to that 1.96. But it also leaves that denominator alone. I've taken care of the denominator here, so it's 98 minus 100. So we just said, okay, so what I have here, oh, let's do it here. This is where we're doing the canceling. Okay, so what I have here is now this standard error times 1.96 equals -2. What am I going to do? I'm going to move that 1.96 out by dividing it, cancels on that side, bring it over to the other side, and divide it over here. Right? So now I have this standard error equals 2 divided by 1.96. It gives me a standard error of 1.02. Okay, so now I can use that 1.02 in my standard error equation to help me figure out what my n is that I have to have that 1.96. So, it's our new equation, right? It's our new standard error equation where the standard error is the 1.02. And that's going to equal that standard deviation of 20 over some n that we don't know. I've already gotten rid of the square root because I'm going to account for that later. Right now, I just want to get n by itself. And so the first thing I'm going to do is multiply it out, cancels on that side, multiplied on that side, so I end up with this n times 1.02 equals 20. We're going to get rid of that 1.02, cancels on this side, going to divide it on this side, so it becomes n equals 20 over 1.02, and that gives me this 19.6078431, but I have to square it because I need to account for that square root of the n over there. So once I've squared it, I get an n of 384.46. But remember, I can't have a decimal of a participant or a part of a participant. I have to have a whole participant. So I'm saying that in order to get a z of 1.96, I have to have at least 385 participants in the study. Okay, let's go ahead and move on to question number 15. Here we're going back to the 4 steps, but then they're going to add in this other thing afterwards. Okay, so let's do one thing at a time here. First, let's see where the 4 steps are going to happen. And we'll begin that by reading the question. It says, the researchers cited in the previous problem also examined the effect of caffeine on response time in the driving simulator. Okay, so let's just know that here when they refer to the previous problem, they're talking about problem number 14. We haven't done problem 14. So, but that's okay. We don't need to know anything about problem 14 in order to understand problem 15. All we're saying is we're looking at some study. We're looking at the effect of caffeine on response time in a driving simulator. Right? Driving simulator is like one of those fake driving apparatuses. And the reason why they have those is they'll like have you do different things in the driving simulator, like maybe come up to a crowded intersection and see what you do in that situation, right? They can simulate the whole thing. Okay, here what they're doing is they're going to see if we give you some caffeine, does that influence your behavior in the driving simulator, right? Like one thing that I would think is the caffeine might make you a more aggressive driver, or it might make you a more speedy driver, driving more quickly. Okay, so in a similar study, researchers measured reaction time, right? Okay, so caffeine can affect that, reaction time. Like this is like how long it takes to react to something. Like so you're in the driving simulator and you're stopped at a red light. Then the red light turns green. Reaction time will be how long before you put your foot on the gas when the light goes from red to green. I think the idea is that the caffeine might make you start to drive more quickly. Okay, so they're saying, in a similar study, the researchers measured reaction time 30 minutes after participants consumed 1 6-ounce cup of coffee. Kind of an interesting study because a lot of people will do this. A lot of people will have a cup of coffee and 30 minutes later they will go out driving. And so it's interesting to see if that does have any effect on their driving ability. Using the same driving simulation task for which the distribution of reaction time is normal, with a population mean of 400 milliseconds and a standard deviation of 40, they obtained a mean of 392 for a sample of 36 participants. Okay, so they're saying normal driving reaction time is 400 milliseconds. That's like 1,000th of a second, right? So 400 of those. They obtained a mean, though, of 392 for a sample of 36 participants, right? So the participants that got the caffeine, their reaction time was lower than the population. Okay, so the first question they're asking is, are the data sufficient to conclude that caffeine has a significant effect on reaction time? In this case, did the reaction time go down? Did they react more quickly? And was it the caffeine that did it? That's what they're asking in question 1. So they're setting us up in step 2, where they're saying use that two-tailed test, the alpha of 0.05. Okay, so let's go ahead and figure out what to do here. Step 1, you are stating your 2 hypotheses. HO is the one that's the null, that's saying that there's no effect. H1 is the one that's saying that there is an effect. How are they saying that? They're saying that actually The average hasn't changed. The population's reaction time is still 400. With H1, they're saying that there is an effect in that the caffeine produced this change where now the population's reaction time is something other than the 400. Okay, so that, I didn't write it down. Let's say that is our step 1. Now we can go ahead and move on to step 2. Right, where we identify our critical region, and basically all we're saying is the Z that we calculate in step 3 has to be greater than 1.96. So let's go ahead and do that. We just know now we're in step 3, right? That equation and that equation. We start off by calculating our standard error, and we're getting that 40 because that's our standard deviation, and we're getting that 36 because that's our sample size. So that reduces to 40 over 6, which reduces to a standard error of 6.67. We're now going to take that standard error and use it as the denominator in our new Z equation. And remember, the Z is the sample mean minus the population mean, sample mean minus the population mean over that 6.67. That reduces to a negative 8 over 6.67, which then reduces to a negative 1.20. Now remember, that Z is the Z that we're going to compare to our step 2 Z. Here what we're seeing is that, right, we're just comparing the absolute values. 1.2 is less than 1.96. When this Z is less than that Z, that is going to affect your decision, right? Our step 4. And the decision that we have to make is that we have to accept the HO. There was no significant effect. Why was there no significant effect? Because the step 3Z was less than the step 2Z. Okay, so now in question B, they're asking us to compute Cohen's D to estimate the size of the effect. Now here what they're saying is it looks like there was an effect, right? The effect that looks like it happened is that this number was different from this number. The sample mean was different from the population mean. There's this difference between the two. So even though there is this difference between the two and it was not significant, we at least want to know what that difference was in terms of Cohen's D. Here, we're saying that the way that we can calculate Cohen's D is the formula is the mean difference divided by the standard deviation. What do I mean by mean difference? It is that difference. The sample mean minus the population mean. That difference. Here, oh, and the other thing that we're saying is that number that we write there is the absolute value of the difference, right? So whereas here it's a negative number, here we ignore the fact that it's a negative number, we're just using the absolute value of the number, right? So there's a difference between these two numbers of 8, and so we just put that here. That means that then Cohen's D is 0.2, which is saying that there's not really much of a difference. Okay, so write a sentence describing the outcome of the hypothesis test and the measure of the effect size as it would appear in a research report. Here, basically, the way that we would write it up, if we were to write this in a report, is we'd say, the results indicate that caffeine had no significant effect on response time, right? It didn't cause it to change in any significant way. We know that because our Z that we got was negative 1.20, and the critical region that we'd identified was where we'd have this probability that was greater than 0.05. We didn't get that, and so that's why we're saying that the results are not significant, and we just then report the Cohen's D as the 0.2. Okay, so let's go ahead and move on to number 17. And looks like in this one, it's basically the exact same thing as problem number 15. Okay, so we're going to run through the 4 steps again. Then we're going to calculate. So the 4 steps are going to be problem A. And problem B, we're going to calculate Cohen's D. And then in part C, we're just going to write it the way that you would write it in a research report. Okay, so one thing at a time. Let's go ahead and read the problem first. A high school teacher has designed a new course intended to help students prepare for the mathematics section of the SAT. A sample of n equals 20 students is recruited for the course. Is it just me, or are there a lot of typos in this book? Right, 'cause I saw one earlier, and I'm seeing one again. A sample of n equals 20 students is recruited for the course. And at the end of the year, each student takes the SAT. Right, so there's a typo in there, but okay, whatever. It doesn't affect our ability to read the question. The average score for this sample is 562. For the general population, scores on the SAT are standardized to form a normal distribution with a mean of 500 and a standard deviation of 100. Can the teacher conclude that the students who take the course score significantly higher than the general population? Use a one-tailed test with alpha at 0.01. Uh-oh, did we do that? Okay. So yeah. Okay. So let's answer question A by going over the 4 steps. First, let me just make sure that we know the important information. Right, so we were given our n of 20. We know that. That's important because that's going to go into the standard error. We know our sample mean is 562, and we know our population mean is 500, and that our standard deviation is 100. Now, one thing I do want you guys to notice here, right, is they're saying that, wow, the students in the sample who had the extra help, right, the new course, they got 562, whereas most students that take the SAT get a 500. So the sample did better than the population. Question is, right, I'm just going to try and draw the curve here. One thing that I'm seeing is that if the mean is 500, right, and the students got 562, they did better than the mean. But notice that the standard deviation is where that would be at 600. So the students are within one standard deviation of the mean. So that's right off just looking at this. This is telling me that if the students are here, right, they are in an area of no significance. We'll say this area is no sig. They shouldn't be counted as doing that much better than the population. This is one where the HO is going to be true. I'm predicting. And the reason why is because if HO were false, then the students would have to be in here, right? So if there really was a treatment effect, the students would have to have some score in this region. Okay, so my prediction, just based on what I'm seeing here, is that there is not going to be a significant effect. But let's see. Let's see what happens. First, our step 1, we're articulating our null hypothesis that says that there's no effect. And basically it's saying that even though the sample got 562, their scores weren't that different from the mean. So in actuality, the population mean is still 500. Again, let's just say the treatment was not effective, if that's the case. However, the other prediction that we're making is the alternative hypothesis, H sub 1, which says that the mean is no longer, the population mean is no longer 500, and that's saying that yes, there was an effect. Okay, so now on to step 2, where we're identifying our critical region. One thing that you want to notice is that we now have a different critical region than we've been given in the previous problems. They said that you're using a one-tailed test and your alpha is 0.01. So what that means basically is you would go look up what z that alpha is, and that z ends up being 2.33. So this now is the z-score that the step 3 z-score has to beat, right? We have to calculate a z-score higher than that in step 3 in order for us to say that the treatment is effective. Let's see if that happens. Okay, so starting with step 3, let's mark 2 equations. First equation is the standard error equation, and I'm saying it's 100 over the square root of 20. I'm getting that 100 because it's our standard deviation. I'm getting that 20 because that's our sample size. That's going to reduce to 100 over 4.47, and that's going to reduce to 22.37. Wow, that's a huge standard error. But in any case, that sets us up to do our z equation. Right, so now the z is the sample mean minus the population mean, 562 minus 500, over our standard error, which is 22.37, reduces to 62 over 22.37, and then we get a final z. What is the final z? 2.77. Okay, so man, I was wrong up here. What we're seeing is our step 3z is greater than our step 2z, right? It's a bigger number here than here. What does that mean? That means that in our decision in step 4, we are going to reject the null hypothesis. We are going to say that there was a significant increase in SAT scores, right? So that the treatment was effective. Wow, that's weird. I'm saying it's weird because our group was within 1 standard deviation. Anyway, we've got our answer to question A. Let's go ahead and see now what happens with question B. All they're asking us to do is compute Cohen's d to estimate the size of the effect. So remember that Cohen's d numerator is the difference between the two different means, right? 562 minus 500 gives us 62. Over 100, remember the 100 was the standard deviation. So now here we're saying Cohen's d is 0.62. That is the measure of the effect size in terms of Cohen's d. So last thing that we have to do is for question C, write a sentence demonstrating how the results of the hypothesis test and the measure of the effect size would appear in the research report. Basically what we would say is the new course had a significant effect on SAT scores. The z that we calculated was 2.77. This happened when we set our critical region at a probability of less than 0.01, and the Cohen's d that we calculated was 0.62. Okay, so as far as the odd problems are concerned, that's where I'm stopping. I'm stopping at problem number 17. The reason why I'm stopping here is because for like the last 3 questions in the book, they take us a step further where we talk about power in the problems. And in my opinion, that's going a step further than I want to go with you guys in this introductory level statistics course. Really, I think it's important that you just understand the 4 steps in calculating the Cohen's d, and that's enough for you to understand the gist of what's going on in this chapter. So that's why I am stopping here. Thank you very much. I look forward to seeing you in chapter 9.